The second part of 13.1 has us utilizing that SOHCAHTOA phrase to help find side lengths and angle measures in right triangles. When solving for side length in a right triangle, you can use the following methods. Yesterday we talked about Pythagorean theorem. As long as you know two sides, you can always find the length of the third side. But we can also use that SOHCAHTOA phrase not just for creating all the fraction answers, but for finding specific side lengths and angles. You'll want your calculator to try and plug this in. Our first example, solve for side length B if angle C is 90 degrees, angle A is 32 degrees, and little c is 17. If we create a right triangle with this information, I'll put my right angle in the corner and label that C. I'm going to put A on the left and B at the top. If angle A is 32 degrees, that would be our theta, or our reference angle. Side length C is 17. There's our given information. Now it says we're asked to find side length B. On this picture, B is going to be that side length at the bottom. From our given information, if we take a look at the 32 degrees, the B and the 17, think SOHCAHTOA. Would this be comparing sine, cosine, or tangent? Well, from that given angle, B is the adjacent side length and 17 is the hypotenuse. That would be the cosine fraction. So we would say cosine theta equals adjacent divided by hypotenuse. For this picture, theta is 32. That means cosine 32 equals the adjacent side, which is B, divided by the hypotenuse, which is 17. Before you plug anything into your calculator, let's get B by itself. If we multiply both sides by 17, the 17s would cancel on the right. And B would equal 17 times cosine 32. Go ahead and type all of that into your calculator now. And you should get B is approximately 14.1. We'll round our final answer to the nearest tenth. So anytime you have a side length and an angle, SOHCAHTOA is a great option. When you're asked to solve for angle measure in a right triangle, you can use these methods. If you know two angles, you can always subtract from 180 to get the third missing angle. You can also use SOHCAHTOA, but in a different way. We'll use the inverse of SOHCAHTOA, and I'll show you where to find that on your calculator. And we'll use that with the following example. It says solve for angle or the measure of angle A if C is 90 degrees, little a is 3.5, and little b is 5.2. Again, if we create our triangle with that information, we'll just draw a right angle over here, a right triangle, over here. We'll put a right angle C in the corner. I'm going to put capital A on the left and capital B at the top. It says little a is 3.5. That will go directly across. Little b is 5.2. That will go at the bottom. So we're trying to figure out how we can connect those two values for angle A. If we think of A as our reference angle, kind of like our theta again, the side length 3.5 is the opposite side length. And the side length 5.2 is adjacent. Looking up at the top of our screen, now which trig function would make sense? We would use tangent. Tangent compares opposite over adjacent. So if we take tangent of theta equals opposite over adjacent and plug in what we know everything but that theta. We would say tangent of angle A is equal to 3.5 over 5.2. To get a by itself, we wouldn't divide by the tangent prefix. We're going to take the inverse. We would say, that's a little arrow right there. Then a equals tan inverse of the fraction 3.5 over 5.2, and I'm off my screen. So on your calculator, you should be able to see the SIN for sine. Right above it, there's SIN -1. You can get that -1 by typing the second button at the very top left of your calculator and then press tan, or sine, cosine, or tangent. So then press tangent. If you do second tan, type 3.5 divided by 5.2. You should get an angle measure for A of approximately 33.9 degrees. And that's how you can use SOHCAHTOA to find angle measures. For now, we're going to omit example 5. We may come back to it later, but we're likely just going to skip it. Let's move down to example 6. It says, find the measure of the smallest angle of a 3, 4, 5 right triangle. So if it says 3, 4, 5, those would be the side lengths. All right, let's go ahead and draw a right triangle. Notice I'm not labeling any capital letters. It doesn't say triangle ABC or angle C or anything. It says 3, 4, 5. So with a right triangle, we know that the hypotenuse has to be the longest side. The hypotenuse then has to be that 5. The 3 and the 4 could be interchangeable. Doesn't matter where we put them. It kind of looks like my vertical segment is smaller, so I'll identify that as 3, and then I'll make my other angle 4, or other side length 4. If we want the smallest angle, the rule is it's always going to be directly across the shortest side. Since 3 is the shortest side, the angle down here in the corner is going to be our smallest angle. And since we know all 3 sides, we can pick sine, cosine, or tangent to solve. It actually won't matter. We haven't worked with tangent or cosine yet, so let's try that one. I'm just picking it for like randomly. So if we say cosine theta equals adjacent over hypotenuse, theta is actually going to stay, cosine theta. The adjacent side length, if we take a look at our measurement or our side length comparison from theta, adjacent is that bottom side, which is 4. The hypotenuse is 5. So in fraction form, cosine theta will equal the fraction 4/5. To get the measure of angle theta, we're going to take the inverse again. So anytime you're trying to find an angle measure, that will require taking the inverse on your calculator. Go ahead and type in cosine inverse of 4 divided by 5 and round your answer to the nearest tenth. Be careful on this one. If you round to the nearest tenth, you'll get 36.9 degrees. That would be the measure of the smallest angle in that right triangle. It's a lot of fun to use SOHCAHTOA to solve word problems. When you're interpreting a word problem, you'll often see the phrases angle of elevation or angle of depression. Notice in the picture, you see a pilot in an airplane, and you see kind of like the landing tower over on the left-hand side. If a pilot is looking down, the pilot is depressing the line of sight. So notice that angle at the top is outside of probably the triangle we would draw in the inside. The angle of elevation would be the people in the watchtower, or whatever you want to call that, looking up towards the pilot. So they would be elevating their line of sight. If you create a triangle, the angle of elevation will always be at the bottom going up towards the top. And angles 1 and 2 are actually equal to each other. If the pilot looks straight out and the air traffic controllers look straight out, their lines of sight would be parallel to each other. So if you know an angle of depression up here at the top, you could create a right triangle by putting that same angle measure down at the bottom for the angle of elevation. Otherwise, use the given information for the word problem and try to generate a right triangle. Label the parts that you know and then default to SOHCAHTOA as a means to solve. All right. Example 7. A plane takes off at an angle of elevation, so here we go with that angle of elevation of 22 degrees and travels for 110,000 feet before it levels off and reaches cruising altitude. Find the airplane's height at that time. So it says the airplane takes off at an angle of elevation of 22 degrees. So let's say this is the runway. The airplane takes off at an angle of elevation of 22 degrees. It says the plane travels for 110,000 feet before it reaches cruising altitude. So let's try to draw a plane here, like so. And that's our cruising altitude. It kind of levels itself out. It asks, what is the height of the airplane at that time? So if I drop an altitude straight down to create my right triangle, I want to know the height of the airplane. So reading through that word problem again, a plane takes off at an angle of elevation of 22 degrees and travels for 110,000 feet before it levels out and reaches cruising altitude. Find the plane's height at that time. Thinking SOHCAHTOA, if 22 is our reference angle, x would be opposite and 110,000 would be the hypotenuse. We would use the sine ratio. If we take sine of theta, which is 22 degrees, that would equal the length of the opposite side divided by the hypotenuse. Pretty easy to get x by itself here. We'll multiply both sides by 110,000. Try to get that to fit over here. And that cancels out. So if you take 110,000 times sine 22, round your answer to the nearest tenth and be sure to label. I got an answer of 41,206.7 to the nearest tenth, and the label would be the length measure in this case, which is feet. And there's utilizing SOHCAHTOA to interpret a word problem. Let's try another one. An airplane pilot spots the runway with an angle of depression of 6.5 degrees. If the altitude of the plane is 34,325 feet, what is the distance between the runway and the point on the ground directly below the plane to the nearest tenth of a foot? So there's lots going on here. So now the airplane's actually up in the air this time. So draw our airplane kind of up here somewhere, left and right, air wing and a wing. The pilot normally looks straight out yonder, but it sees the runway with a line of sight, or an angle of depression, of 6.5 degrees. That's a pretty small angle, or it should be. And the pilot sees the runway. So pretend the runway's down there. If the altitude of the plane is 34,325, altitude is height. And that would be the perpendicular height to the ground. That's 34,325. And that label is feet. It says, what is the distance between the runway and the point on the ground directly below the plane? So that would be this distance along the bottom. So it's not the distance the plane would travel to reach the runway, it's the distance along the ground. So that 6.5, remember, is an angle of depression, and it's not on the inside of the triangle, but it should be the same as the angle of elevation up towards the airplane. That would be 6.5 as well. So if we think SOHCAHTOA, once again, what trig value would compare our reference angle of 6.5 with opposite and adjacent? That would use tangent. So we start off by saying tangent of our angle, which is 6.5, equals the opposite side length, which is the height of the plane, 34,325, divided by the adjacent side, which is x. So we run into a little bit of trouble here. When x is in the denominator, we can't just divide by 34,000 because x would stay in the denominator. So what we need to do here is a little cross multiply. I'm going to put tan 6.5 over 1 and then multiply crisscross to get rid of the fractions. If I take x times tangent 6.5, that would equal 1 times 34,325, which just stays the same, 34,325. So now, to get x by itself, we'll actually divide the tangent away. So tangent of 6.5. So not just tangent, but we're taking the angle with it. On the right, tangent 6.5. So I'm going to make my screen a little bit smaller so that I can get this problem to fit over here on the right. Let's go ahead and plug that answer in. 34,325 divided by tan 6.5. Did you think you'd get an answer that big? It's actually a pretty big distance, isn't it? 301,266.7. And our label, once again, would be feet. Oh, nope. Yep, that's right. 301,266.7 feet. The plane is still quite a ways away from the runway. All right, let's move on. We have two more. What is the angle of elevation of the sun if a 52-foot tall tree casts a shadow that's 85.5 feet long? All right, so we're looking for the angle of elevation. We have to be thinking SOHCAHTOA inverse. We have a tree that's casting a shadow. So here's the height of the tree. The shadow would be down here. Hopefully we'll conclude the tree is perpendicular to the ground. If the height of the tree is 52, and the shadow, I don't know why my fives are so goofy today, and the shadow is 85.5 feet, the angle of elevation is always the angle that goes up towards the top. So that would be our theta value. What trig definition would we use here if we think SOHCAHTOA? If our angle's at the bottom right this time, the height of the tree would be the opposite side. The 85.5 is the adjacent side. We should use tangent here. Tangent of our angle is equal to opposite over hypotenuse. And to get theta by itself, we're going to take tangent inverse on our calculator. Tan inverse of 52 divided by 85.5. All right, go ahead and type that in, see what you get. Hopefully you got approximately 31.3, and our label for angles is always going to be degree. All right, one more. A surveyor stands 115 feet from the base of the Washington Monument. The surveyor measures the angle of elevation to the top to be 78.3. So this one's kind of nice. The picture's already drawn for us. How tall to the nearest tenth is the monument? Taking a look at this picture, I see my reference angle down here at the bottom. We're asked to find the height of the monument, which is opposite that angle. And we know that the surveyor is 150 feet away, which is the adjacent side. So we have another opposite and adjacent. We would use the tangent ratio. Tangent of the angle that's formed, 78.3, is equal to the opposite side, which is the height, divided by the adjacent side, how far the surveyor is away. So this one's a quick and easy one to solve. To get y by itself, let's multiply both sides by 115. And you should get that the height of the Washington Monument is approximately 555.3 feet tall. So there's utilizing a little bit of right triangle trigonometry to solve some real life application.